For problem number 30, you want to notice that you do have a polynomial divided by a polynomial. Anytime that is your situation, what is question number 1? That could be question number 1. Question number 1 is that numerator lower degree, or, that a question of that nature. Because otherwise you need to start this problem with division and then see where it goes after that. And as far as the checklist is concerned, check. Then, second thing, look at that denominator. Can we factor it? How much can we factor it? What you should notice about the denominator is you have a constant term. You have a term with the function x squared. And you have a term that is that x squared function squared. Anytime you have some function and then that function is also squared, and then there's a constant, and that's all you have, it is a quadratic form. And in that case, you can factor it in the normal way you would factor, except that normally when you're factoring, you set up x's, but when it's a quadratic form, whoever the function is that is sitting in one term and squared in another term, that function is who leads it. And then with a leading coefficient of 1, you're finding two numbers that multiply to make positive 2 and add to make positive 3. So I think we got this one. Woo! Factored. And those are two quadratic factors that cannot be factored any further. So now what do we do? It's time to decompose. Fraction decomposition. See if you can remember how to set that up and how to get it started. And I'll give you a moment to see what you can do on your own. So with two quadratic factors, each one as its lone denominator needs to have a less degree polynomial above it, which would be linear. Then I need to multiply both sides by the denominator. Let's try that again. And then in this situation, it's probably ideal to expand the right side. I'm going to distribute the ax through the x squared plus 1. And then I'm going to distribute the b over the x squared plus 1. And then I've got that plus sign. And then distributing the cx over x squared plus 2. And distributing the d over the x squared plus 2. And then the terms that have an x cubed are a plus c. For the x squared, b plus d. For the x, I have a plus 2c. And then for the constant, I have left over b plus 2d. On the left, the polynomial does not have an x cubed term, so its coefficient of x cubed is 0 x cubed. That means a plus c must equal 0. And then b plus d is going to have to be equal to 3. A plus 2c is equal to 1. And b plus 2d is equal to 4. And now the mission is to solve the systems of equations. I am going to bring the b plus d equals 3 over here and subtract. B minus b is, whoops, I apparently can't write the letter d. There we go. B minus b is 0, 2d minus d is d, and 4 minus 3 is 1. Woo! If d is 1 and b plus d is 3, b must be 2. And then I'm going to bring a plus c over here equals 0. And I'm going to subtract the equations. A minus a is 0. 2c minus c is c. And 1 minus 0 is 1. And then if a plus c is equal to 0, then a must be negative 1. Wasn't that nice and fast? Now, my integral has turned into ax plus b would be negative x plus 2 over the denominator x squared plus 2. And then cx plus d is x plus 1 over x squared plus 1. And finally, it's time for integration. Yes, I am recording. And I want to, as much as possible, do less trig substitution, because trig substitution leads to trig integrals, and I want to keep the trig integrals down a bit so I don't have to bring in too many trig identities. So I want to look for how much can use substitution take. For this first integral, if I were to make a u, my u would be x squared plus 2. And I look at its derivative. Now, because x squared plus 2 does not have that middle term with the x, the derivative is just a constant multiple times x. And in those situations, you just flat out split the numerator. And so you can see for the second one, we will do the same. So now I'm going to write out 4 integrals. I can see the use substitution that I'm going to use on the first integral. For this third integral, I'm going to use a use substitution of the denominator. See if you can stay ahead of me on those use substitutions. My x dx is replaced with 1/2 du. And this negative sign I'm bringing outside of the integral, and then it's the integral of 1/u du. And natural log of absolute value of u, I don't have to have absolute u because x squared plus 2 is positive. So there's one integral down. Let's look at this third integral with its use substitution. X dx is replaced with 1/2 du. And then all I have left is 1/u. And the integral is natural log of u. And my third one is integrated. Let's look real quick at the fourth one. Do you recognize the fourth integral? If you don't recognize that fourth integral, you can go through trig substitution and then go, oh yeah. Or you recognize it. What is that integral? There we go. That is arctangent of just plain old x. The only thing I have left now is the second integral. And I'm going to bring that integral over to the side. And let's integrate. I need to do a trig substitution. My function being squared is x, my number being squared is root 2, and I am adding, I have a sum of squares. When I have a sum of squares, I want to use the tangent function to equal the function being squared divided by the number that is being squared. Using my triangle knowledge, opposite over adjacent is tangent. Then Pythagorean theorem finds me the third side, square root of x squared plus 2. When we have u, we need du. So we take the derivative of tangent, and derivative of tangent is secant squared. And take the derivative and multiply by differential dx. Oh, my dog is snoring. I'm going to try to put the microphone over and see if you can hear it. Was that audible? Yeah, he's a bit quiet. We just envy him right now, don't we? Okay. So that also gave you a little bit of time to maybe get your integral set up. And most people find it easiest if they prep some of this. I have my dx, and most people will try to figure out what is x squared plus 2 based on this triangle. If I use the side that has the square root of x squared plus 2 and the side that has the constant, and I write it in that order of hypotenuse over adjacent, that's the trig function secant. If I multiply root 2 over to the left and square both sides, I will get 2 times secant squared theta is equal to my x squared plus 2. And now I finally have that the integral changes to 2 over 2 secant squared theta multiplied by dx, which is root 2 times secant squared theta d theta. I get some cancellation, I get some more cancellation, and all I have is the square root of 2 d theta. The integral is root 2 times theta. Theta is inverse tangent of x divided by root 2. So that was inverse tangent, and I've already forgotten, of x divided by root 2 multiplied by the constant root 2. And then don't forget plus C. Doot, 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 doot. Yay! I'm going to stop the recording of this problem